Okay, welcome to section 3.6, the chain rule. The chain rule allows us to take derivatives of more complicated functions. So I'm going to start off by giving you an example of a problem that we would have a little bit of trouble doing without the chain rule. Let's say that you're trying to do the problem 3x plus 5 to the power 2. Now in order to get this, according to the rules you know so far, you would need to maybe multiply this by itself. So it'd be 3x squared plus 2x, so 2 times 3x times 5 plus 5 squared. So this would be our original function. Now we're not finding the derivative yet, we're just writing down the original function in expanded form. And this of course is 9x squared plus 30x plus 25. And then we could find the derivative. Okay, so that wasn't very difficult. We have 18x plus 30. And there it is. Okay, now let's go ahead and write this as 6 times 3x plus 5. Now if you look closely at the answer, you'll notice it has a 3x plus 5 in it, in the same way that the original function had a 3x plus 5 in it. If you look at this even closer, you realize that we used to have 2 powers of 3x plus 5, but now only 1 power of 3x plus 5. You might even be able to figure out where the 6 came from. The 6 in the front, if you write it as 2 times 3, it would look like this. So where did the 2 come from? Where did the 3 come from? We can see the 3x plus 5 to the first. Turns out, and you may be guessing this already, that the 2 is the original 2 from up here, and the 3 is the derivative of the inside part. Okay, now I'm going to go with that example again, this time with a little bit more elegance. Let's say that we were given this problem. Let's just go back in history here. Let's say we were starting off with this problem here. Could we really just do the following? Treat it as a function that is a square and a function that is 3x plus 5, sort of at the same time. Well, let's break this down. Let's say that we take the 2 from the upper register here and bring it out front and change it to a 1. Now this is what we would do with 2x squared, right? Or excuse me, this is what you would do if you had, let's say, just x squared. You would bring the 2 down and you would change the power to 1. Now we're not dealing with just x here. We've got a 3x plus 5. But if we leave the 3x plus 5 there and bring the 2 out front and change the power to a 1, so far it feels like we're just taking the derivative of a monomial. Okay, now having ignored the inside so far, maybe we should take the derivative of that also. The derivative of 3x to the 5th is simply 3. So could it be that the answer is simply 6 times 3x plus 5? And we already saw that the answer to that question is yes. Okay, so this really makes you wonder if we can go even further with that. What if we had, let's say, 2x plus 1 to the 4th power? Okay, so the conjecture is that maybe the derivative is as simple as bringing the 4 down and then having 2x plus 1 now to the 3rd power and then multiplying by 2, which is the derivative of the inside. Could the answer really be just 8 times 2x plus 1 cubed? Well, let's take a look. Okay, so let's say you did this the long way. Now Pascal's triangle allows us to expand things to the fourth power, binomials to the fourth power relatively quickly. So it would just be 1, 4, 6, 4, 1 for coefficients. Okay, and for our 2x's, we decrease the powers. So you remember doing this in algebra 2. So 2x to the fourth plus, and then 4 times 2x cubed plus 6 times 2x squared plus, and then 2x to the first plus, and then in the last term we have no 2x's. Okay, and then working backwards, starting with this 1, we work backwards. We're putting in a 1 to the fourth at the end, right? A 1 to the third here, and a 1 squared there, and a 1 to the first, and then we do not have any 1s on the opening term, the leading term. Okay, so all of this turns out to equal y equals 16x to the fourth plus, and then we have an 8 times 4, so 32x cubed plus, and then we have a 4 times 6, which is 24x squared plus, and then we have 8x plus 1. Now it turns out if you factor this down, you can actually get this to come out to 8 times 2x plus 1 cubed after we take the derivative. So let's take the derivative. Okay, so we take the derivative, it's 64 x to the third plus 96x squared plus 48x plus 8. And remember, the derivative of that 1 is just simply 0. We could factor out an 8, and we get 8x cubed plus 12x squared plus 6x plus 1. And believe it or not, that factors nicely into 8 times 2x plus 1 cubed. Very interesting. Okay, so now we haven't proven anything. We haven't proven that our little trick works here with the chain rule. But if it does work, and it turns out it does, and it turns out that it can be proven, it's just not something we're doing today, we should be able to do a problem like 2x plus 1 to the 100th power in under a few seconds. So if this was our function, y prime would simply be 100 times 2x plus 1 to the what? 99th times, and then the derivative of the inside, 2. The answer is 200 times 2x plus 1 to the 99th. Okay, very impressive. Alright, now let's take a look at some trig examples. Let's say that you started off with, and we're going to switch to the f of x notation here. Let's say that you started off with f of x equals, and then we had sine 2x. And you wanted to find the derivative. Okay, well, one thing that might be good to remember is that this function can also be written as, it's also known as, aka, 2 sine x cos x. Now I bring that up because right now we don't know how to find the derivative of sine 2x, but we do know the derivative of sine x and cosine x. So this identity provides a nice workaround prior to learning the chain rule. Okay, so let's go ahead and take care of this. So we have two functions. We have 2 sine x and we have cosine x. Alright, so 2 sine x, we're going to take the derivative of that, times the second function plus, and then the first function times the derivative of the second function. Okay, so this turns out to be, what's the derivative of 2 sine x? Well, the 2 can come out. So we haven't talked too much about the rules for differentiation, but one of the things we did say is that you can factor out a coefficient. So I don't know if it was necessary to rewrite this step, but just to convince you that it's okay to do that, you can bring this 2 out to the front. Okay. So what is the derivative of sine x? We've talked about that. That's cosine x. And so we have actually cosine x here. What's the derivative of cosine x? Well, that's just negative sine x. So we end up with 2 cosine squared x minus 2 sine squared x. Okay, now you may or may not remember the following identity, but if we take a 2 out, we have cosine squared minus sine squared. Now we know cosine squared plus sine squared is 1, but actually cosine squared minus sine squared, you can look it up, is cosine 2x. Okay, so let's look at our answer. Could we have gotten that faster? Well, it is no surprise that we ended up with a cosine in the answer, because we started with a sine. And we know that the derivative of sine is cosine. So we ended up with cosine in the answer. Okay? In fact, it's not just cosine x, it's cosine 2x, which kind of makes sense because we actually started with a sine 2x. And we ended up with a cosine 2x. Where did the extra 2 come from? This 2 out in front of our cosine 2x. Well, it turns out that that is the derivative of the 2x. Okay, so what you have here is basically the derivative of the cosine being the derivative of the sine, and this 2 out front is the derivative of the interior. So this is actually d dx of the 2x, and this is dd ddx of sine x, so to speak. And we can't use x here, it's actually a 2x, but what we typically do here is we'll say that this is like a u. So this was some function, it was a sine of something. It wasn't sine of x, it was sine of 2x. But being sine of something, the derivative of sine of something is cosine of something. But it looks like it's not just the derivative of sine of something is cosine of something. It turns out that the derivative of sine of something is cosine of something times the derivative of that something. Okay, you will get the hang of this. It's actually pretty easy to learn, even if it's nested several times. Let's look at another one. Okay, let's take a look at this problem here. Let's say that you had sine of 4x. And let's just make up a new name for the function h of x. Okay, now we know the derivative of sine is cosine, so we're wondering if we can just kind of jump into this answer here. So we have a sine 4x. I suppose the derivative would involve a cosine 4x. We also have a 4x, and the 4x needs to be differentiated. So the derivative of 4x is 4. And there's the answer. Let's do another one. Let's say you had t of x, which is equal to, and let's do cosine of 3x squared minus 2x plus 8. The chain rule states that the derivative will be a sine, a negative sign actually, times, or excuse me, sine of and then it will be this same expression on the inside. So the derivative of cosine of something is negative sine of something, and then times, and then the derivative of that something. Well, the something in this problem, we call it the u, is 3x squared minus 2x plus 8. So the derivative of that something is 6x minus 2. It is that simple. Okay? Let's step it up a notch. Let's say that your function is tangent squared x. Okay, so this is a little bit different looking. It might be helpful to write this as tangent of x quantity squared. So this reminds us of that problem we started with for the chain rule when we had something squared. So the first thing you would do is bring the 2 down. 2 times, and now it's just tangent x to the first. That's not a derivative, that's the first power. Times, okay, now we've got to get the derivative of the inside. The inside is tan, so the derivative of that is secant squared, and that is the answer. Let's do another one. Q of x equals, let's take the tangent squared example, and let's beef it up a little. Let's put 3x to the 5th minus 2 root x. According to the chain rule, q prime would be, let's go write this as tangent of 3x to the 5th minus 2x to the half. We'll write it in power notation, exponent notation, squared. So this power is this 2 here. Oops. Okay, so this is supposed to be 1/2. Sorry about that. And all of this is squared. Okay, so let's see what happens. Okay, so the first thing we have to understand is that it's a power, it's something with a power 2 on it. So we're going to bring the 2 down. The inside part, the tan, and the expression within the tangent is now to the first power. So I won't write the first power. Well, I'll write it, I'll erase it. So first power. Okay, I don't want you to think it's a derivative symbol, a prime. Okay, times, and now the derivative of tangent. Now the derivative of tangent is secant squared. So we have secant squared 3x to the 5th minus 2x to the half. So we just took the derivative of the inside, but not fully. We haven't dealt with the innermost function, which is this one. 3x to the 5th minus 2x to the half. So it's the final step in the chain, the final link in the chain, you could say, is to find the derivative of that, which is of course 15x to the 4th minus, and then bringing the half down cancels with the 2, so we just have 1, and then it's just x to the minus half. And there it is. So that one was 2 compositions in one. Notice we started with the outermost function, so that was this one, and that's where this 2 came from, right? And it's also why we have this tan again, but with a first power on it. Okay, and we have the derivative of the tangent part, which is secant squared, and then finally we have the derivative of the inside, which is over here. The structure is very important, but you'll get used to it. It isn't hard to learn at all. Okay, let's factor out a negative cosecant. Let's factor out a negative cosecant from this part, and we'll bring it all the way out to the very front. So we factor out a negative cosecant. I get cosecant x, so the negative cancels with this negative that was out front in the beginning, times cosecant x plus cotangent x all over cosecant x plus cotangent x squared. Okay, so this term is right here. So that was just on the bottom. Okay, and then I factor out a negative cosecant from the term that I underlined here. Right, and it canceled with this negative one up front. Okay, so the reason I did this is because you can see how this would clean up. This would cancel out with one of the factors of cosecant x plus cotangent x down below, and the answer can actually be written pretty nicely as CSC over CSCx plus COTx. And this can be written in terms of sines and cosines as well. But that's pretty clean. Okay, I lied. One more example. Sorry guys. This one's pretty important. So let's say that your function is x over the square root of 1 plus x squared. Okay, so again, it's important that you write things in a way that's more power friendly, more like an exponential. So we'll keep the x to the first, and we'll put times, and then this bottom part we can write as 1 plus x squared to the minus half. Okay, so we need the times to imply. Alright, so what we have here is two functions now. We have x, and we have this one. So we first recognize, hey, this is a product, okay? Not a chain rule problem, not right off the bat. It's a product. Okay, so when it comes time to find f prime of x, you can set this up as 4 parentheses. And something tells me that I'm going to end up needing some more space here. So I'll fill it in as I go. We'll start off with 4 parentheses. And put in some more space there. So your parentheses may be pretty full here, right? As we've seen. Okay, so the first one actually isn't though. The first is just the derivative of x, which is our first function. That's just 1. Okay, gave myself too much room for that. Okay, the second one is the original function 1 plus x squared to the negative half. I'm not modifying it. In the product rule, remember, you leave the function as is while you differentiate the other one. Okay, so that was just basically the derivative of the first one times the second function. Okay, now we switch it up. Now we keep this first function times the derivative of the second one. Okay, so we just did the first function, now we're going to do the derivative of the second one. Okay, now we're doing the chain rule, right? So bring down the 1/2, the negative 1/2. The 1 plus x squared now has the power negative 3/2. And we multiply by the derivative of the inside, which is 2x. 1 plus 2x. Or 1 plus x squared has derivative 2x. Okay, let's clean this up real quick. So actually the radical notation, I will stick with power actually. So this is going to be 1 over 1 plus x squared to the half. Right? Plus. And then we have a term here that's going to go on the bottom. Actually, it's technically not that whole thing I circled, it's just this part. that's going to go to the bottom, right? Now there's a 2 down there as well. That's this 2 here. Okay, so it's going to look like this, minus 1 over 2 times 1 plus x squared to the 3/2 times, and then there's this 2x here, that just goes up top, so I'll just fill in a 2x there. And then I need a common denominator. Okay, so I'm going to come over here, I'm going to multiply this by 2, top and bottom. Actually, what am I doing? I'll just reduce this. I won't erase it, I'll just cancel it. Okay, then I won't need a common denominator here. Okay, so let's just combine these now. So multiply top and bottom of this one by 1 plus x to the first. And the reason I'm doing that is because that's going to give me the 3/2 power, because right now I only have a 1/2 power. Okay, so I'm not going to put the 1 power on there. I'm just going to write 1 plus x and 1 plus x multiplication. Okay, so we end up with 1 plus x minus x all over 1 plus x squared to the 3/2. And these cancel out. And we end up with 1 over 1 plus x squared to the 3/2. And then don't try to distribute that power or anything. That's your derivative. Okay, the last topic for the day is parametrics. Okay, parametrics. So you might remember studying this in pre-calc. You would be given something like x equals 3 cosine t and y equals 3 sine t. And you're asked to generate a table. It wasn't an xy table, it was a txy table. And you would pick familiar values of t, specifically reading angles that you could find, so that you could be plugging in here. Okay, so you'll pick a value of t, so let's say 0, and that would be plugged into both of these expressions. Whatever you get are your x and your y. Okay? And then you'll actually be plotting those. Okay, so let's say you plugged in 0. You get 3 cosine 0, right? And 3 sine 0. So the point that would be plotted is the point 3 comma 0. This is an x and a y. See? Okay, and then you could plug in the next one, maybe like pi over 4, let's say. Pi over 4 would be 3 times cosine pi over 4, 3 times sine pi over 4. Close parentheses. In other words, 3 root 2 over 2, 3 root 2 over 2. And then the next maybe it might be like pi over 2, and you get the hang of it. It's going to be 3 times cosine pi over 2, which is 0, 3 times sine pi over 2, which is 3. So you would plot the point 0, 3, and so on. Okay, it turns out that if you do that, you end up with a circle with radius 3, centered right on the origin. Okay, so you can draw it if you like. This is what ends up being traced out if you're willing to plot those points. Okay? Okay, and what's really satisfying is when you realize that had you squared those two equations to begin with, and added them, you would have ended up with x squared plus y squared equals 9 cosine squared t plus 9 sine squared t, which in turn, if you factor out the 9, is just 9, because the cosine squared plus sine squared is 1. Now, had I written it like this, you would have realized it was a circle right off the bat, centered at the origin, radius 3. But it was written in what we call the parametric form. Okay, now, we know for sure that being a circle, it is not, doesn't have any sharp turns or anything. So we should be able to pick any point on the circle and find, and be able to draw a tangent line. Some of those are horizontal, some are positively sloped, some are negatively sloped. There's even a couple of vertical tangents on here, which means there are, at these two locations specifically, the two vertical tangents, it is not differentiable. Now this isn't a function anyway, so I wouldn't say something like this function is differentiable. It's not a function. What it is it's a parametric representation of two functions. We have the top and a bottom of a circle, both of which are semicircles. Those semicircles are functions. Okay, so I don't want to get too into this, but what I'm trying to say is we should be able to find the derivative of this. Okay, now had I given it to you in this form, finding the derivative would require some new skills. But giving it to you in this form, there is a way to quickly find the derivative, and here's how it works. To find the derivative, you would take the derivative of the y divided by the derivative of the x. Okay, so if you wanted to find the derivative of the slope of the tangent lines, I shouldn't probably write m. Kind of done with m, aren't we? The derivative is going to be, and let's go ahead and use dy dx on this, okay? It's going to end up being dy dt over dx dt. So for like this problem, you'd be taking the derivative of 3 sine t, which is simply 3 cosine t, all over, and then the derivative of 3 cosine t, which is of course just negative 3 sine t, and the 3's would cancel, and you would just actually get negative cotangent t. And there it is. So this is a new rule. I'm going to go ahead and write it on the next page. You can pause it and copy that if you like. I'm going to move the page. Here's the rule. dx dt, I'm sorry, dy dx, if your function is given in parametric form, can be found by doing dy dt over dx dt. And this, of course, assuming that dx dt is not 0, otherwise you couldn't be dividing here. It also assumes that we don't have cusps and corners and those sorts of things. So this assumes differentiable functions x and y. But those ones I gave you were sine and cosine. Those are perfectly continuous and differentiable. New rule. Okay, so for a quick example of that, we could say, what is the equation of the tangent line? To the curve y equals, x equals, so you get two of them, so you get x equals 6 CSCT, and a y to go with it. Y equals 3 SECT at t equals pi over 4. Okay, so it's very simple. You're going to be finding dy dx when t is pi over 4. So we'll just take the derivative of y first. Very important. Okay, don't do x on top. Slopes always involve rise, right, on top. Okay, so this is a ratio of two derivatives. So, and dx dt goes on the bottom. Okay, so it's going to end up being 6 times, or excuse me, 3. See, I almost put the x on top. So we're doing the derivative of 3 secant t on top. So the derivative of that is 3 secant t tangent t, right? And the derivative of 6 CSCT, excuse me, is 6 times, and then it's CSCT COT negative. Okay, so this reduces to 1/2. And we can write this simpler, but our goal was to plug in pi over 4 anyway. So okay, so here it goes. It's secant pi over 4 times tangent pi over 4 all over -2 times CSC pi over 4 cotangent pi over 4. Okay, so the secant of pi over 4, you do your homework there, it's root 2. Tangent of pi over 4 is simply 1. Okay. Cosecant of pi over 4 is also root 2, and cotangent of pi over 4 is 1. So the answer is -1/2.